Okay. Now, first of all, so first we want to still talk about this convergence for our weakly hyperbolic groups. And then we're going to talk about the Poisson boundary. Right. And so the setting here it was that X is a, yeah, maybe non-proper separable delta hyperbolic metric space. Okay, we take O base points, we take G a group of isometries, and we take mu a non-elementary measure. On okay, and so the goal here was, the goal is to show that for almost every sample path, the limit as n goes to infinity of W and O converges in this boundary. And recall, so the boundary of X is the Gromov boundary. So intuitively is the space of rays emanating of a point from a point up to identifying two rays that fellow travel each other. Also, we define it also as a space of Gromov sequences. So Xn in X Gromov sequences. We saw last time how to do it formally. But of course, the intuition is still what we said at the beginning, that we start with O and we look at geodesic rays and we identify two rays where when they are bounded distance from each other forever. Okay, and then as we recall, the issue here was that this Gromov boundary is not compact in general. And so we cannot produce easily a stationary measure. So the intermediate goal was to produce a stationary measure on this space. And then more or less the same proof that we already saw for the disk more or less works. So the other point was to define this Horo function compactification. Okay. And recall basically the definition is like this. So we have this map from the space into the one Lipschitz maps that vanish at O. And the map is indeed Z goes to rho Z of X, which is D XZ minus. So we normalize it so that it is a 0 at O. So the way we need to do it is that if we plug in X equal O, right, we have to counteract this. So this is a space of functions, and so the Horo function compactification is, as we said last time, is the closure of the image of rho X, closure in this space of functions. And the real trick here is that the topology here is the weak topology. So with the topology of pointwise convergence. So this is the most important trick in this. However, we realize that the topology of, so in this case, X, and so differently from that one, this one is always compact, metrizable. So this one is metrizable, it's still metrizable, it's metric, let's say, in the sense that we have a metric that we know we want to use this metric, which is the metric of fellow traveling. Two rays are close to each other if they fellow travel for a very long time. So this one is metrizable. We don't care what the metric is, but we care it's compact. Also, there's an action. So there is an action. So G acts on the space of Horo function. So again, an element of this is some function, and we're gonna call it a Horo function. And so there is an action which is like this. So G acting on H. So if H is a Horo function and G is a group element, GH at a point X is H of G inverse X minus H of G inverse O. So it's kind of the obvious thing. You act on the space, you look at the function, or you have to take G inverse by the fact that you want an action. And this one is just to make sure that this still is zero at zero. So there is this action, and this action is by homeomorphism. So this action is by homeomorphism. So the important corollary of all this is that there is a stationary measure. So there is at least one stationary measure mu on X for H. And the reason of that is just simply the compactness of this. So the proof is, again, the space of probability measures on this compact space is also compact. For the weak star topology, and in particular, well, you want to solve the equation mu star nu equals nu. You're given mu, and we're going to solve this fixed point equation. And we already did it. We already figured out how to do it. You take basically any measure, you take the push forward repeated convolutions of this, and you take the Cesaro average, and you take a limit point. And the limit point exists because of the compactness.
When you look at the space of probability measures, do you always take what is it? You take the Borel sigma, you fix the Borel sigma algebra, right?
Yeah. I mean, this again is a compact metrizable space. So yeah. So it's as a topological space, is just as good as any compact metric space. So it comes with the topology, it comes with open sets, it comes with the sigma algebra of Borel sets. That's right. So that's why I insist on separability, because if it's not separable, well, again, maybe something can be done, but then you go into this more hairy situations where the space of probabilities on a space which is not Polish or something, then it gets slightly more annoying. But this is just as good as any other compact metric space. Yeah. Okay, so that's good. Now the question is, though, what is this any good for us? Like, okay, we could have more than one. Eventually, we'll see that it's unique, but we can have more than one.
So
yeah,
the separability for the space.
Right. So the separability tells you this is metrizable.
Oh, okay.
Yeah, if this space is too big, yeah, then this would not be metrizable. This is too big. Yeah.
But didn't you say that separability is not
A posteriori, you can play a trick if you have a countable group that acts on a delta hyperbolic space, even if it's not separable. You consider the orbit of G. You can take something like the convex hull of the orbit, and this would be separable. So yeah, so posteriori, if you have so G is a countable group, you can it always act in a sense, it always acts, but you have to use the delta hyperbolicity to say that this convex hull is somewhat invariant by the group action actually. But yeah, that's right. But this object, if X is separable, is always compact and metrizable. We're not using delta hyperbolic here at the moment. Okay, so now, yeah, is this any good for us? What so we don't care too much about the convergence in that space. In fact, the Random walk does not converge in the Horo function compactification. This is another strange fact. So W and O does not converge in. And again, our favorite counterexample is this ladder space. So imagine again that you have a group, your group is something like Z times plus minus 1. So, you know, with a certain probability, you can flip from the upper stair, from the upper part of the stair, the ladder to the lower one, and so forth. And so remember that the boundary of this space has 4 points. So if you're assigning some definite probability at this to this one, then it's kind of annoying because then it will keep going, flipping lower and upper infinitely often, and you will not converge to a point in there. So the convergence is only verified once you quotient and you get to the Gromov boundary. Yes?
Is the Gromov boundary always a quotient of the Horo?
It is. It is. In fact, this can be made very precise. But first, let me first. Yes, that's right. So, okay. So what we need? So we need a map from the Horo function boundary, or at least, yeah, to the Gromov boundary. In fact, if we take the Horo function, the whole compactification, well, you have the starting points are inside the space, so you want to map from the whole compactification to this modification. And obviously, another thing we would like this map to be is G equivariant. That would be certainly good. Probably not so expensive, because if everything we define is natural, it should come out equivariant. And some form of continuity, even though cannot be really continuous, because this is compact, this is not compact. So this map cannot be globally continuous. On the other hand, to transfer measures from one side to the other, you need a certain level of continuity. Yeah. And so this is the next object, and it's called the local minimum map. So before doing that, let me see this example, which is not just it will be really essential for the next lemma. So let's just discuss this example. So if X is the reals with the usual metric, Euclidean metric, then what is X bar? H. Well, again, if you think about what is a Horo function, so let's think about let's draw some sort of the graph, right? So this is the R direction, and this is H. Like this is the values of H. So right? So a Horo function, so okay, we pick the 0 somewhere. So every Horo function vanishes at 0. So the finite ones, well, the finite ones look like this, basically, are V-shaped. And the minimum of those, right, is at, right. So if this is row Z, the minimum is at Z. So that's the original functions that we define. It's a distance function from Z and it's scaled so that it's 0 at 0. So it's a V-shaped function. Now, what happens if we take a point as limit of V-shaped functions? Well, two things, there's two options. Either the limiting point is still inside, and then you just converge to another V-shape. So if Zn converges to Z inside R, so they have a sequence, then okay, rho Zn converges to rho Z. So the limit is still a V-shaped function, right? But what's the other thing that could happen? It could happen that Zn goes or either all the way to the right or all the way to the left, right? And so you can immediately see that there's two more options. So if Zn goes to plus infinity, well, rho Zn converges to something which is not a Horo function of this type. Let's call it h plus infinity. And what is this? Well, you can tell, right? So if this point keeps going to the right, the minima keeps going to the right, yet at 0 it remains at 0. So the limit is simply the function that goes down linearly forever, just decreasing line. So we associate to this function the point at plus infinity. And then clearly there is another, mirror case, which is when Zn goes to negative infinity. Then you can clearly tell that the limiting function is what? Well, is the increasing one. So if Zn goes to minus infinity, then rho Zn goes to h minus infinity. And what is it? Well, again, it's 0 at 0. And then it's increasing linearly along the real axis. So these are all of the options here. That's clearly nothing else. So in this case, we can say that the compactification is R union plus infinity and minus infinity. And again, in this case, we are in a good case, so to speak, that the compactification is the same as the Gromov boundification, because that's the same for the Gromov. Okay, now if we have an arbitrary so now we take any Horo function. So this lemma, and now we are starting to use the delta hyperbolicity somehow. So again, x is delta hyperbolic. And then we say let gamma a bi-infinite geodesic. In X. And now we take, so now let's any h in the Horo function compactification is of either, satisfies either one of the two things. So we want to say, what is the restriction? So you take your space and you take gamma is this geodesic. And now you want to know what is the form of this function? Okay. And so there's two options. So either there is P in gamma such that h of x is h of p plus the distance from x to p plus r of delta. So here we always have, so for every x in gamma, or there is p again, such that, well, you're actually going either one way or the other. So h of x is h of p, but here we have the distance with a sign. I call it d plus xp plus r of delta for every x in gamma, where d plus is the signed distance. So, in fact, there's two choices associated to one of the two orientations. Yeah, associated to one of the two orientations of gamma. So what does it mean? It means the following, that for each h, there is a point, let's say P. So either we are in the first case. What is the first case? The first case means that the function is going up in this direction and in this direction linearly. So this P is the minimum point. If you take another x, the function is just going linearly, so it's V-shaped. So that's the first case. It just goes up. The second case is like this case is, I don't know how to call it, is what, no letter like that. It's a slash shaped. It's like it goes, the other option is the function goes up, keeps going up as you keep going along the geodesic. So, okay, whatever we choose for P, it's not really that relevant for 2, because we pick some point and then we know that the function is going up along the geodesic. It could go up along the geodesic this way or down. So it could go, that's why we say one of the two orientations. So it could go either up this way or up the other way. So basically the same thing that happens for R, it happens for any delta hyperbolic. So here we use the delta hyperbolic. In fact, yeah, this O of delta is very much related to the hyperbolicity of the space. And we use it.
But in this case, you don't, like, case 1 doesn't need to correspond to a point inside the space.
It does not.
Yeah.
Yeah, that's right. Yeah,
maybe that's the point of the compactification, right?
That's
like
the point of the compactification, indeed. That's right. So it could be that some limit point is not, in this case, is not that H is rho of Z for some Z inside the space. We don't know yet. You don't know at all. It's not the case. It's not true. But it could still be that the limit has a minimum inside. Yeah, that's right. In fact, the proof of this is pretty simple. We can even say it like that. So you have gamma, and so you see that you say that H is the limit of certain sequence rho of Zn. And so we pick a sequence Zn, and we let Pn be the closest point projection of a closest point projection onto gamma of Zn. So basically we take the closest point on gamma to Zn. And what you have to realize is that by hyperbolicity, so this is a point, if this is another point x, Yeah, so by hyperbolicity, basically, if you take, yeah, if you do rho Zn restricted to gamma is basically a rho of Pn plus O of delta. So basically, it's because you have this sort of reverse triangle inequality. You take a point X, and whenever you want to study the distance from X to Zn, well, since this is the closest point projection and the space is hyperbolic, this is like, it's basically this. So the distance between X and Zn is the distance between X and Pn plus the distance between Pn and Zn plus O of delta. Yeah, this is where the thin triangle comes into play. And we have to say, we have to pick Pn to be the closest point projection for this to be true. It's not true for any point, but in this case, it is true. So yeah, if you, yeah, you can think of this angle being right angled, even though there's no right angles in this metric context. And so clearly, yeah, if you rewrite this, you see that if you rewrite rho Zn, it's like dxzn, and so you always basically you simplify this. Yeah, this happens twice, and so you get that the restriction of rho Zn to the geodesic is basically a rho of the projection. And now we can clearly see what happens because, again, there's two changes. Either Pn tends to some P, some point P inside, or it doesn't, or it goes to infinity. And then if it goes to infinity, it goes to infinity in one of the two directions. Then, right, either, well, okay, it also, this space need not be complete. So it could be that Pn doesn't really converge, but it's still bounded. So everything is up to O of delta. So we can eat all this small things. So right, so basically either Pn converges to P inside gamma, or Pn can go to plus infinity or to minus infinity. And so this corresponds, so this one corresponds to H belongs to the case 1. And the second one is that H belongs to the case 2. Any questions about this?
So we don't really need hyperbolicity, just some sort of projection.
Well, pretty strong form of projection. You want a reverse triangle inequality. So pretty strong form of projection. I mean, you want this to be additive. So sure, I mean, yeah, good luck. I mean, yeah.
Oh, I see. I see it.
So yeah, I mean, I don't know if this is equivalent. I suspect that if we make it strong enough, it might be equivalent. But okay, yeah, a priori it's not equivalent, but this is a pretty strong form.
Yeah.
The projection has to be really well controlled. Yeah. 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 So for instance, I don't think this is true for cat 0. So okay, so and now the other thing that we can gather from this discussion is that, okay, so there are two options. So we say a Horo function is finite, H in X bar H is finite if the infimum of H is not infinite and it is infinite. If the infimum of H is infinite. Minimum is for sure negative because yeah, at zero. So wait. So all right. So if H is finite, then we can define the minimum set of H to be, well, coarsely, the set of Z in H such that H of Z, well, it doesn't have to be equal to infimum. Okay, we can have some fudge there, but it's less or equal that, for instance, the infimum of H plus 1. So this is a set. Not quite the point, but what is really nice here is, yeah, the lemma which follows from this classification is that there exists some C which only depends on delta, such that the diameter of this minimum set is uniformly bounded by C to any H. So that's the cool thing. Is that, okay, well, this is a set, but it's small set. It has always the same bounded diameter, and in fact, the C will depend just on the delta of hyperbolicity. And the proof of this is precisely this idea of looking at the minimum. So you suppose there are 2 points. So X and Y are in mean H. And suppose they're very large. The distance between X and Y is very big. So, okay, we can make precise this immediately in a while. So, okay, so now you take the geodesic. So take gamma geodesic between X and Y. Okay. So, okay, say they lie in this geodesic. There is H, X, and there is Y. But now, what shape can this Hura function have on this geodesic? Well, the Hura function only has 2 possible shapes, as we just proved. It's either V-shaped, or it's increasing in one of the 2 directions. But neither of those is compatible with this path, because, right? So let's say you have X and Y. Well, how can the minimum be at X and at Y at the same time? Right? If the minimum was at X and was at Y, what does the function look like? There is no such function. This would have to be W-shaped or something. There is no W-shaped Hura function. Right? Of course, you can make it V-shaped if you want by doing it like this, but then this is the minimum. It's no longer either of those. And right, and these Hura functions, they grow linearly. So, right. Yes.
So then wouldn't the minimum just be 1 point by this argument?
Well, everything is up to O of delta, right? I mean, everything is up to O of delta. You have no control in the very small scale. So yeah, no, it's fine. I mean, the Hura function could be something like that. Yeah, that's fine. It could be that those have distance 1, which, yeah, delta. Yeah. If the distance between the 2 minima is bounded by delta, that's fine.
Right, because it's not a Hura function on the line. It's just
Yeah, exactly. For the line, we are sure that this is the only thing because really we just have precisely the metric structure. But here the metric structure is always somehow up to this all of that. So okay, very good. So this is very nice. So this, in fact, will define a map from the finite set of Horo functions to some subset of X. But now, how about the infinite Horo functions? And so for that, we need another lemma, which is I also find kind of cool, which is, so if it's an infinite Horo function, we take sequence of points that such that the value of the function goes to infinity. So before that, let's state the following lemma. So for each base point O and each H, each is a Horo function, and each xy points X, we have the following inequality, then the minimum between minus H at X and minus H at Y, bounded above by the Gromov product of X and Y based at O plus of delta. So this is a preliminary lemma that will tell us what we need to know about the infinite Horo functions. So let's see how to prove this. Maybe this is easy enough to be proven. So it's a good exercise to play with definition of Gromov product. So remember what is the definition of Gromov product, right? So the Gromov product between X and Z at O is the distance between O and X plus distance between O and Z minus distance between X and Z over 2. And in fact, just this and the triangle inequality would imply that this is less than distance between O and Z minus distance between X and Z. Let's see, why is this the case? Now, this is just a triangle inequality, and you simplify a few terms, right? So you bring the 2 on the other side. So these 2 beats this one, so you get rid of that. You have a minus 2, you get rid of that. Yeah, so this is equivalent to DOX bigger or equal than DOZ minus DXZ. So that's just a triangle. Okay? So clearly, you could guess why on the right-hand side I want to put that. Yeah, this is the Horo function. So this is minus rho Z of X. Okay? So this does not require the delta hyperbolicity. What does require the delta hyperbolicity is the following, which is another equivalent characterization of delta hyperbolicity we didn't discuss, but it's this, that if you have X, Y, O is bigger or equal than the minimum between X, Z, O and Y, Z, O minus delta. So this is sometimes a way to, in fact, even to define delta hyperbolic spaces. This is equivalent to the thin triangle condition, that you have some sort of ultrametric inequality, let's say, for the Gromov product. So this is not true in general in any space, but it's true in delta hyperbolic spaces. Basically, okay, you have X and Y, right? And this is the Gromov product And then if you have another one, yeah, this is bigger than the minimum of the two. So basically, if you take, another point Z, and you look at the geodesic from X to Z and the geodesic from Y to Z, there has to be one of the two has to be closer to the origin than the white one. And the reason is this triangle is thin, in fact. So this is an equivalent characterization of hyperbolic spaces. So if you trust me on that, we can complete the argument by taking the limit, right? Because here, what do you get? Well, yeah, you combine these two things. You see that xy L is bigger than the minimum of minus rho z x and minus rho z minus delta or O of the, okay, maybe this is not delta, but O of delta true. So yeah, so that's it, because now you take the limit. Now take limit as z, Zn goes to something, right? Any Horo function is the pointwise limit of this function's rho z. So when you pass to the pointwise limit, whatever the pointwise limit is, you're gonna keep this inequality, right? Then you get that x, y, 0 is bigger than the minimum minus h of x minus h of y. That's any h. And again, we just have to test 2 points. That's why the point test convergence is enough for this kind of computations. That's kind of neat. So why is this neat? Because now we think of the following. So suppose let H be an infinite Horo function. So what does it mean to be infinite? Well, it means that the infimum is negative infinity. So then, well, by definition, there exists a sequence Xn such that the infimum, that H of Xn goes to negative infinity. This is just by default. Now, what is really neat about this setup is that we claim that this sequence Xn does converge not only in the Horo function compactification, but in the Gromov compactification. So then, what we can claim is that Xn converges in the Gromov topology, in the Gromov boundary. And moreover, the limit is unique. In the sense that does not depend on a particular choice of Xn. So this is particularly satisfying. It's like, okay, you have a sequence x1, x2, x3, any sequence. We just have to say that for this sequence, the value of the given Fourier function goes to negative. So the lemma tells you that this sequence does indeed converge to a boundary point. Moreover, that there is no actual choice involved in here, meaning that if I pick another sequence, y1, y2, y3, that has also the property that h goes to negative infinity, it also converges to the same point. So this is kind of miracle, I think, but it's true for because of this lemma. So the setup somehow is very robust to these definitions. So the proof, yeah, it's really using this. So the proof is the following, right? So since x goes to xn goes to negative infinity, well, let's take the Gromov product between xn and xm. Well, this is less or equal than the minimum, right? Or it's bigger, sorry, bigger, yeah, so the Gromov product is bigger than the minimum of hxn, hxm plus O of delta. So clearly this goes to infinity as, let's say, the minimum of m and n goes to infinity. The limit, yeah, the limit from this goes to infinity. So xn is a Gromov sequence. And then why is it unique? Well, because again, if also you take another sequence, hyn, that goes to negative infinity, well, you can compare them, right? So we would have that xn, yn at O is bigger than the minimum. I guess minus here because we go to infinity. So minus h of xn minus h of yn plus O of delta. This also goes to plus infinity. And this is exactly the definition that we gave of equivalence between Gromov sequences. So they converge to the same point. Right, so the limit as n goes to infinity of xn is the same as the limit as n goes to infinity of yn. So just by this setup and this classification theorem that we have of Fourier functions in delta hyperbolic space, then we can produce this map. And in the end, right? So in the end, what do we get? Well, in the end, we get, so we can define the following. The local minimum map and this is a function from the Fourier function boundary to, yeah, so basically it's either in the boundary or not quite x, it's like it's a subset of x if you want. But it's the subsets are, let's call it, I don't know, PCX or PCX are the subsets in X such that I have diameter uniformly bounded by C. So it's almost points, but not quite. And how do we define it? So if H is finite, we define phi of x, phi of H is again is the set of Z such that H of Z is less than the infimum of H plus 1. And then if H is infinite, we define phi of H to be the limit of n goes to infinity of H x of xn if H of xn goes to negative infinity. And so what did we prove? The first lemma shows that in the finite case, this set has uniformly bounded diameter. So you can think of it as a point in the space, even though technically it's not, but it's basically, coarsely it is. And in the second case, we take a boundary point. So this is a point in the boundary because we take any sequence such the value of the order function goes to negative infinity, it converges in the Gromov topology, and the limit does not depend on the particular choice of xn. So we have defined such map.
This map is exactly like the PML map that goes to the simplices in the curve graph union, its Gromov boundary.
What is the BMO?
The PML is the compact the measured lamination.
ML. Oh, I see.
Right, like you select either a simplex in the curve graph or a point in the Gromov boundary, and like it's exactly the same setup. Yeah. Like you have a compact space and it covers simplices in the curve graph union as the Gromov boundary.
Mm-hmm.
Yeah. That's just a comment, yeah.
Yeah. No, I understand. Yeah. Just this is just a general setup. Yeah, but you're right. Okay, good. So that's very good. So now we unfortunately we still have, so we have to check one thing. So in fact, if we call xf the set of H in X bar such that H is finite and X infinity is H in H bar such that H is infinite. Then what? Then, right. So then it turns out the following lemma, but yeah, we will not quite prove. So phi restricted to X infinity is in fact continuous. So phi globally is not continuous because of what we said last time. So we said that you could pick, remember, the not phi from X bar. So phi globally is not continuous because we recall last time we said that if you have this infinite hydra kind of thing, then you can then you can you see that the limit of this minimum do not converge in the Gromov sense. So so this is the problem, but fortunately, if we just sort of in the end we kind of get rid of the final. So in fact, here is, but what can we like? Can we safely get rid of the Horo functions? So that's the other thing. Get rid of the finite Horo functions. Well, the answer is Yes, because we have another lemma. The lemma is, again, if nu is nu stationary on the Fourier function boundary, then nu of the finite Fourier functions, call it xf, is 0. Yes?
Are the finite ones just in bijection with actual points in X?
No, that's the thing. No, that's the thing. So this is wilder. Yeah, maybe if the space is cat minus 1, something like that, yes. But otherwise, no, because you can again, you can take a limits of objects that sort of, yeah, coarsely stabilized, but they're not, yeah, they're not really, they don't really correspond to points.
Which one's bigger?
Sorry?
Which one is bigger?
Yeah, x is bigger, I think.
X is big.
So whenever you start with a point in x, you can produce a Fourier function.
Yeah.
What?
Oh, X
Yeah.
is bigger.
X is smaller, yeah, exactly. X is contained, yeah. That's right. So this set is sort of, and it's like, yeah, it does not really have a good explicit description. It could be bigger than X, but it doesn't matter because, yeah, in the end, we use it to make sure that, yeah, to produce this compactification, but eventually we kind of discard it by showing that the map, the measure is actually supported only on the infinite ones. So that's the whole point. So to do that, yeah, so this one, we need that if position, and yeah, here we need that mu is non-elementary. I mean, this is naturally coming like, yeah, this is coming naturally because it's a bit like what we just already did for the disk to show that, for instance, the compact subsets of the disk don't carry the stationary measure when you have just a non-elementary measure on PSM2R. That's a similar idea, but okay, now the space is non-proper, so it's a little bit more tricky to prove. Yeah. So in fact, the proof, yeah. So this uses the following lemma.
Sorry, what does it mean to be non-elementary? I forgot. Maybe it came up.
Non-elementary means that the support contains two independent loxodromics.
Okay, yeah, thanks.
So you will see this lemma is kind of, yeah, it's simple. Yeah, it comes all the time. So under these situations, so under nu be mu stationary and so forth, suppose that, yeah, so G acts by homeos on M, some space M, and nu is nu stationary on M, and right, there exists some sequence epsilon n of positive numbers. So this is a sequence of positive numbers, non-zero, really positive, such that for every f in G, so actually, yeah, there is a sequence, there is a sequence of Gn in the group such that this translates out disjoint, such that Fy G inverse of F, G1 inverse of Fy, and so forth, Gn inverse of Fy are disjoint. So that's where the non-elementary will enter. And for any Gn, there is some m such that if you look at the nth convolution, you say n of Gn, this is at least epsilon n. Then nu of y is 0. So, okay, there are many choices to be made in this lemma. Maybe we can see immediately how to apply. Maybe that's the easiest part, and then we can prove the lemma. It's not that complicated. It's just using the stationary properties. So maybe, yeah. Okay, so let's call this lemma 1 and lemma 2. So let's see that lemma 2 implies lemma 1. So how do we see that? Well, we have to take y. So in this case, y is the set of h, which are the Hora functions, such that the minimum phi of h, the local minimum of h intersects the ball around O of radius some r. So pick some big R. So you see, this is a bit like the ball in the disk, except the space is the space of Hora functions. So we take all the Hora functions that have minimum at the finite minimum, and this finite minimum intersects this big ball. So this is B, and then all the minima are somewhere in here. So of course, if we show that all of those have finite and F0 measure, that's enough, because the growth, the union of those over R is the whole of finite Hora function space. And so now we just have to check to use the non-elementary to find such thing. So basically, what do we want? We want that this translates are disjoint. And we use this loxodromic element to produce. So the idea is we use a loxodromic element to move the ball off of it, of itself, and to produce this guys. So, okay, so we pick another f. So, okay, it doesn't matter, right? So Fy, so for f in G, okay, what is Fy? Well, it's another ball, right? So this is it's still a bounded set. It's just because we're just going off by f. So that's not a big problem. So what do you do precisely? Is like this. You say, you choose G, a loxodromic isometry, loxodromic in G, such that the translation length is bigger than 2R plus C. So this C is the diameter of the Hora functions of the minimum that we chose to depends on delta. So we can do this because the measure is non-elementary, so it contains at least one loxodromic element. So loxodromic element means it has positive translation length. If you take a power of it, we'll have a very, very large translation length. So basically, it's an element that will translate this off itself. Well, it's clear that it will translate this off itself by the triangle inequality, right? Because basically, the translation, so this is R, this is also R, so 2R plus something which is given by the diameter of this set, which is C. Okay. And so what do we need to say? So we want to say that so for any f, the sets g to the minus n fy over n are disjoint. Again, we start with the ball center at 0. We apply f, so we get a ball center at f. Oh, okay. The diameter is all this r, and g translates by more than 2r plus c. So you're in this picture. So there could not be a Hora function that has a minimum in here, because this will have c, and there will be r, 2r and c. So 2r plus c should be smaller than that. And so can we apply this basically? So yeah, so we just want to say, yeah, we just have to find this epsilon, but epsilon can depend on n actually, so that's not a problem. And yeah, we have to find mu star, so okay. So yeah, so we say that since the semigroup generated by the support of mu, okay, let's assume here that this is equal to G. Yeah, then for each n, there exists m such that mu star, yeah, mu star m of Gn, which we set to be epsilon n, is positive. Yeah, we have a lot of freedom. So basically for any n, yeah, here we have a lot of freedom. So for any n, we can choose m, and we can choose this epsilon n. So we really have a lot of freedom. The only uniformity that we need is that we have uniformity over f. But that's not a problem, because again, translating a ball by f gives another ball of the same size. So by the lemma, we get that mu of y is 0 for every r. Questions about the proof?
The existence of such m is just because G is...
Yeah, because this is the semigroup generates the whole of G. So for each element in the semigroup, there exists m such that this is positive. Right? That's the definition of semigroup, right? So Gn is in the semigroup. So what's the semigroup generated by the support? The union of the supports of mu star m.
Yes, okay. Yes.
Yeah, that's classic. Yeah, that's right. So here, yeah. So yeah, so okay, so that's the classical thing. So yeah, so now we can maybe finish by saying that. So maybe, yeah, maybe we can prove this lemma too, which is not too hard actually. So yeah. Are you happy with that? Okay, so let's see, can I write them? Yes. So let's see the proof of lemma 2. Well, this is slightly, well, it's basically the usual definition of, it's the usual trick of taking the highest weight element and applying the stationary condition. But okay, it is a bit more subtle because, yeah, it's sort of an infinite, slightly more infinite version of it, but it's more or less the same. So we let S to be the supremum of the measure of Fy, such that Y is in G. This is positive. Suppose this is positive. We want to find the contradiction. Right? So we want to prove that the measure of Y is 0. So we take all the orbit of Y, and we take the supremum of its translates, and you suppose that this is 0. If it's, and then we want to get to contradiction. That's how it works. So let's see. So we write again the stationary condition, basically. So we choose n bigger than 2 over s, and epsilon is the minimum of this epsilon I. So this could be like, yeah, the soup cannot be, maybe it's not achieved, but basically the point is we can take finitely many, and we're kind of close enough to the soup. So that's the general idea. So now we have to choose these various quantities. I'm sorry if there's a little bit of notation here, and then you can choose f such that nu of Fy is bigger than S minus, yeah. So okay, we have epsilon like this, and we call epsilon S is epsilon over this big F. So this, and then we at some point for any epsilon, including for epsilon S, there is some F such that this is bigger than S minus epsilon. Okay. And then we know that there are G1, Gn such that they are disjoint. So G1 inverse F1, Gn inverse F1 are disjoint. And for any n, there exists some m such that mu star mu of Gn is bigger than epsilon, because we pick epsilon to be the minimum of the first n. So basically the basic idea is, okay, there's infinitely many such elements, but okay, we take the supremum, and it's enough to take 2 over s such elements. And once you have this finitely many, you can reason with just finitely many. That's the idea. And so, yeah, so unfortunately, there's a little bit of notation, but it's not too bad. So, okay, so the new stationary says, new stationarity says the following: that nu of Fy is the sum of mu star H nu of H inverse Fy. This is literally the definition of mu stationary for the nth convolution. That's fine. And so, yeah, now this is so yeah, there is a big one. This is big. So in this sum, there is one which is very big, which is the first one. And so let's see how about the others, right? So for G, in G, we can write like this. We can write mu star Mg, nu of G inverse Fy is nu of Fy minus everything else. H in G different from G of mu star H nu of H inverse Fy. And so each of them is bigger than S minus epsilon S. This one is, so this one is bigger than that. And then how about this ones? Well, let's see, right? So the supremum is S. So each of those is at most S, right? So this is at least minus, well, it's S times the sum of the measures. Okay. And the sum of the measures is 1 minus, right, mu star of G. So this is S. Yeah. So this is S times 1 minus mu star M of G minus epsilon S. Because the sum of the measures is 1 minus. Oh, sorry. So that's, sorry, there's too many minuses. Sorry, no, there's yet another one. Sorry. So is S is still there, minus. Okay. Okay, so now now we can write it. So S minus S is done. So this is S mu star mg minus epsilon S. And then we can divide by this. So we get that nu of G inverse Fy is at least S minus epsilon S mu star mg. Okay. So this is true for every G, basically. So in particular, we pick these ones that give rise to these joint things. So basically, they're all so again, what is the usual thing? We take the maximum weight by harmonicity. The other weights also have to be close to the maximum. And so basically, the whole thing has to be constant. This is the usual idea, and this is a quantitative version. So we're not at S, but we are off by this much. Right, and so recall, what do we recall? We recall that mu star M of GI is bigger than epsilon. So this is the epsilon that we picked here. So we know that mu of the sum of GI inverse Fy over I equals 1 to N is at least N. N times what? N times S minus epsilon S divided by epsilon. Unfortunately, we chose things kind of rightly so, right? So we know that epsilon S over epsilon is 1 over N. So with this, we chose it before. And NS is bigger than 2. That's the other thing that we chose. So this is bigger. So NS is bigger than 2, strictly bigger. And N epsilon over epsilon is 1. So minus 1. So obviously in the union, the measure cannot be bigger than 1. So this is the contradiction. So again, the idea is we have a stationary measure. We pick a point, we pick it and translate it as the maximum possible measure. And by the stationary condition, the other ones in its orbit also have to be somewhat quite big measure anyways. But the other condition, they are disjoint. So if you sum over all of them, well, you get too much measure. That's basically the point. And the thing is, you have infinitely many elements to play with at the beginning. So you can pick this n big enough, like based on one s. Okay, so this is the technical lemma. Are there any questions? So from here we can somewhat almost finish the proof of the convergence, because we basically already figured out most things. So proof of convergence. So what is the proof of convergence? So recall that there was this game. The game used to be that, so we look at the probability space on the boundary, we find a stationary measure, and then we apply the martingale convergence theorem. And by the martingale convergence theorem, there is a limit in the space of measures. And then by the geometry, we know that the limit has to be a delta mass, basically. And if there's two, there cannot be two different limits, because this would correspond to converging to two different delta masses. So that's kind of that's the outline of the original proper space proof. And for the non-proper space is quite similar, but now we have to go to the Gromov boundary, and so the first thing was, so we consider the local minimum map. So this is phi from x bar h into PC x intersect unit. So let nu be stationary on x bar h. And so what we proved, so first of all, we proved that nu of xf, the finite ones, is 0. So the measure is supported actually. So recall that xh is xf union x. So the measure actually happens to be supported on the infinite part. Now this is good. Now the second part is, so then the map phi restricted to x infinity is a map from x infinity to just the boundary. This one is continuous. And so we can put nu tilde is the push forward. So it's very important that you push forward by a continuous map to get a measure. Yeah, this is something people overlook, but if you overlook, you get something wrong. So the category is of continuous maps with this, in this. Recall a measure is a space, is something in the dual of continuous functions. So we push forward nu. And so this is new stationary on the boundary vector. So finally, we are able to produce a measure that is stationary on the Gromov boundary, even though the Gromov boundary is not compact. But we are able to do it by push forward eventually. Okay, and now the proof is somewhat similar. It's not completely the same, but I think we will gloss over the differences. So it is still somewhat similar. So then we have a martingale convergence theorem. So again, we have to do it in the compact space. So we look at the usual compact and again metrizable. So we need the separability and so forth, because again, we need that the space of functions is generated by countably many such continuous functions. So here again, we define xn of f as the integral of f with respect to the wn nu on the Horo function boundary for f in C infinity of the Horo function. Okay. So so again, we can apply the martingale convergence theorem exactly the same way, precisely because this is a martingale, exactly like we did, and so there is a convergence, and again, the space is not too big. So almost surely, W and nu converges to nu omega, omega. And this, again, is a probability measure on X bar. And again, the convergence here really uses this compactness and so forth. So it's very nice that we can have this space here. But now, once again, we push it forward. So by pushing forward, so this is 4. It's by pushing forward, we get that if you start with W and nu tilde, well, this converges to nu tilde omega in P of X. Again, almost. Okay, so this one, from the compactness and the martingale convergence, we know that in the space of measures there is a convergent measure, a limiting measure almost surely. And now the geometry should tell us that the limit is unique and it's a delta mass, and that would be enough to say that the walk converges. However, there's also another issue here, which is since the boundary is not compact, it also could be that there are sequences that just don't have any limit point at all. So we need to prove that. Okay, I'll write this down. So we need to show that for almost every sample path, there exists a limit point of rho Wn in XH bar. So it does exist a limit point. So mind you, limit might not exist, need not exist. So it does not converge, but there is at least a limit point in this code. Again, this is a compactification, and the space is not too complicated in the sense that since the space is separable, you can find some sort of net, some countable net, so that there has to be somewhere in this net some limit point. So this again uses the separability of the space basically. So I will not go into that detail, but it's important because in principle there could be no limit point whatsoever. that would be a problem, of course. Okay. And now we use the geometry. So by the geometry, by the delta hyperbolicity, there is a similar. Yes, almost every sample path Wn has a subsequence Wnk such that Wnk nu star converges to a delta mass. So lambda is a geometry. So this argument we already did, in fact, basically last time. So the argument was basically, I mean, yeah, basically we showed that every point except for at most one point converges to the same lambda by hyperbolicity. So the idea was something like, if you have two different limit points, you draw the geodesic between them. And then you have that everything inside the geodesic converges to this point. So the whole geodesic enters here, but on the other hand, this point and this point will converge to two different points, lambda 1 and lambda 2. And then this would break the fact that this is a geodesic. So this argument we did in detail for the disk, and it's the same proof. Okay. And so finally we're ready. So we're on the last step. So the last step is to put really together all this discussion. And so the last step is that since the limit exists, since the limit, again, exists almost surely by the martingale convergence theorem, it's not just the subsequence that converges, but it has to be the whole sequence that converges. So again, the probability tells you that the limit exists, and the geometry tells you that any limit point is a delta mass. And these two things combined tell you what is the limit. So since the limit exists, then almost surely the limit has to be a delta mass. Because we know there's always a subsequence that converges. And so every subsequence converges to the same limit. Okay, and lambda is on the boundary. And then finally you could say that then this implies that W and O also converges to lambda almost. Yeah, this is another, I mean, delta hyperbolicity thing. I mean, if the measure converges to neighborhood of lambda, again, every point inside the space, you pick any point. Let's say O is on a geodesic between lambda 1 and lambda 2. And then both lambda 1 and lambda 2 converge to the same limiting point. right? So this is, and so O also has to converge to the same limiting point. I mean, this is there. This is Wn over 2. This is Wn over 1. Okay, so that basically does it. So that shows that almost surely, in fact, because the limit depends on the sequence. And as a final corollary, what we can say is that nu is the integral of nu omega dp omega. So for almost every sample path, we're taking this limiting measure that we know it exists. And since everything was stationary, at every step, the average of these measures was nu. And now if you take the limit, the original measure is still the integral now on infinite paths of each of these measures for each path. And so as a corollary, so the stationary measure is unique. Stationary measure is unique. Because this argument started with just any arbitrary stationary measure. And we can carry the whole thing. And at the end, we say, okay, the random walk converges and the distribution of the random walk is this nu. And of course, and then basically the distribution and the random walk is unique because it's just determined by the random walk. And so in the end, the stationary measure. Okay, very good. So that's more or less the outline of the whole proof. Are there any questions or comments? Yeah. Yeah.
If the limit point, if we have the weird case where it's just inside the space.
Yeah, that's right. But since we know that the stationary measure does not charge the inside, basically it could happen, but you can still intersect. Yeah, basically you just intersect with the set of points that converges to x infinity, which has measure 1.
So we get rid of the measure 0 set.
Yeah, we get rid of the measure 0 set. That's exactly right. Yeah, exactly. Okay, very good. So yeah, next time, which is the last one, I will talk about the Poisson boundary identification, and then next week we will have the presentations. I think I sent the schedule already yesterday, so you should have the schedule. Okay, good.